Welcome to today's session. My name's Stephen Ledig. I'm a Principal Solutions Architect with the Serverless team out of Australia and New Zealand. And thanks for joining us this morning. Hope you're all having a nice time at reInvent, learning loads. Today what we're going to really be focusing on is how to design serverless architectures, but also with resiliency in mind. So I want to get started with a bit of a quiz, just to warm everyone up. I know it's the first session of the day, probably. What's more important? You're in a company, you're selling widgets. Is it more important to send 1 million $1 widgets, or is it more important to sell one $1 million widget? Now, if you're looking at this from a numbers perspective, maybe losing 1 or 2 or 3 or 4 $1 widgets, that may not necessarily be a big deal. But you definitely don't want to be the person that loses that $1 million widget, do you? And this is just to say there's a cost associated with resiliency, right? In 2023, Gartner actually put some numbers towards this. There's a significant financial cost associated with message loss, with downtime that is associated through unreliable systems. And that cost is not just financial. That cost is also impacts your brand and the confidence that your customers have in your products. And so what we're going to be talking today about is resiliency from a serverless perspective. Quick show of hands, who's building serverless apps today? Wow, a lot of you. Okay, awesome. So we're going to look at some of the lessons that we've learned over the years, and particularly those that we've derived from the well-architected serverless lens. I'm going to show you some of the tools that we have available for you to be able to build more resilient systems. We're going to look at some of the serverless-specific, or service-specific, I should say, resiliency strategies that are already built into the services that we have, as well as looking at some patterns around building resilient applications. Now let's level set our definition around what resiliency means. So this is the definition that you'll find in many places. It's the ability really to resist or recover from disruption related to any kind of infrastructure, dependencies, any kind of misconfigurations or transient network issues. And if you're familiar with the shared responsibility model for security, you may be surprised to, or not surprised to learn that we also have a shared responsibility for resilience. Now, with this shared responsibility for resilience, it's very much the same as the security one, right? AWS is responsible for all of the infrastructure that all of your services run on. You're responsible for really performing all of the necessary resiliency tasks around configuration management for things like EC2. You need to worry about distributing those applications or those instances across multiple availability zones so you get high availability. You might be looking at self-healing strategies around auto-scaling and potentially looking at highly available RDS instances or databases that can nicely recover from failure. And a lot of this stuff is things that you have to worry about. Now, from a serverless perspective, AWS is still responsible for all of the infrastructure that runs the services and that are offered in the cloud. But here we're working with largely managed servers that do a specific task. And that changes the landscape a little bit from my perspective. It puts more emphasis on the actual applications and how you compose them, because all of the resiliency stuff, like the auto-scaling, the high availability, multiple AZs, etc., all of that is already taken care of for you from the managed service perspective. And that leaves you the ability, that gives you the focus to focus on the application architecture and the code that you're running on top of those services. And this is fundamentally to say that serverless is really about building solutions. It's about taking those managed services and composing them in a way that helps drive business outcome. And it's important to really point out here that serverless infrastructure is actually an extension to your architectural design patterns, right? It helps you implement the patterns that make your applications work. And that's what's fundamentally distinct from a serverless perspective. Now, true resiliency still requires, and that brings us to fundamentally the topic that we're talking about today. True resiliency really requires deliberate design choices at an application level, not just at the infrastructure level. Now, who's seen this before? Everyone's seen this. This is our typical serverless architecture, which we've been telling customers about. This is quintessentially a microservice, right? And I feel that this is a bit of a naive example, but it's one we're going to be working with today, just to sort of drive home some of the point. Because really the reality is that customers today are building far more complex systems. And when we look at all of these lines, there's a lot of stuff that we kind of like take for granted. And I just want to dive into this a little bit more. Now, this is this is a toolbox. Like I look at architectures quite a lot from lots of different customers or lots of different industries. And this is the one thing that I really come back to. So if you don't learn anything else today, just remember this. Because this is the one thing that's going to help you understand or actually like just raise questions about some of the assumptions that we make about the lines in our architecture. So this is the two-box in a line architecture that Gregor Hoppe popularized a couple of years ago. So you may have seen this before, but it's a really good exercise to ask yourself, what assumptions can you make about how these two services or how these two components are actually integrating with or interacting with each other? I'll give you a little moment to think about it. You might be asking yourself, what's the interaction model? Is this an asynchronous or a synchronous integration? Is this representative of a point-to-point or a pub-sub kind of architecture? It's pretty hard to tell, isn't it? What about, is B polling A? Are these two components distributed? Are they even in the same account? We don't even know. What about the data format? What about the conversational state? How is that being managed? What about error handling? What happens if, if B is calling A and something goes wrong, right? Are there retries implemented? Do we have partial failures? Do we have exponential backoff? Like, what are the assumptions? Does B need to be idempotent? We'll talk about idempotency in a little bit. So there's a lot of questions that you could ask yourself about how your services are interacting, and when we're drawing lines, we can't always make assumptions. We'll get into a little bit about that in a bit. Now, if you're like me, one of the things that are constantly hammered home to you is this whole idea of loose coupling, right? And making sure that your applications are loosely connected, however, have good cohesion. And when we dive into this a little bit more, we realize that there's lots of different facets to coupling, right? We've got technology. There's technology coupling. We've got spatial dependencies around where do things live? Do we address them through IP addresses or DNS? What impact does that have on our applications? We look at things like temporal coupling, right? This is probably one of the biggest things that you're going to be dealing with from a serverless perspective because of our ability to deal with asynchronicity. But it's probably fair to say that there is no such thing as loose coupling. In fact, it's not in the extreme. Right? There's no loose or tight coupling. It's really just a function of multiple dimensions where you're making trade-offs. And so you need to make some decisions around where you want to put the most effort in terms of making your applications more loosely coupled. So going back to our example around what microservices looks like, is this a resilient architecture? Now, when I'm looking at this, maybe some things you might want to think about are, does the client really need to actually, wait for a response? What kind of, what happens if there's a surge in traffic in the API? How do I protect my backend? Lots of little questions that come up. What about my database, right? Have I configured it correctly? What happens if there's any failure in the database transactions when I'm writing my records to that? So it kind of always leads you to these questions like, was that the $1 million widget that I just lost? Understanding what the impact of these questions are. So in order to get to this point, we need to start thinking about what could possibly go wrong in serverless, right? One of the first things that we as developers we need to know is like, what are the service limits and the quotas that are associated with that? Quite often you might think you're on the right path. You might be going, okay, I've got a Lambda function writing something to DynamoDB, but the function is timing out. Or there's some error rates that are unknown or maybe look like are coming from Lambda, when in fact what you've really done is misconfigured the read-write capacity for DynamoDB. The other thing you might want to look at is, the other thing that causes errors within serverless are things like misconfiguration. Incorrectly defined IAM permissions, probably one of the bigger challenges for many of us. Resource availability is potentially another one. And state management is also an area where we can potentially get into strife. But one of the things that I kind of like to focus on is making sure that we've got appropriate design decisions. Sometimes our assumptions around how we connect the dots and how we put solutions together is really what the main problem is. Things like function chaining, for example, right? Having one function connect to another, call another function, calling another function. These are anti-patterns within serverless that you should really try and avoid. Now, anyone who's familiar with the well-architected program knows that it's based around these 5 pillars. We've got 6 pillars now, sorry. And from a resiliency perspective, what we're really going to be focusing on is the reliability. Now, the well-architected framework is a great tool to help you sort of better understand your operational environment and what you're doing from a governance perspective, with the idea of just focusing on particular applications. But sometimes we don't go deep enough, right? And this was the case for serverless a few years ago when we introduced the serverless lens, which was specifically designed to try and dive a little bit deeper into what is actually happening at an application level. And we've come up with a whole heap of best practices around some of the more common pitfalls that customers might fall into, and provided a whole heap of guidance, which includes things like this around observability, which is really what sort of kicked some of this stuff off. Giving you advice around not just trying to measure the nuts and bolts of or the mechanics of how an application fits together, but also understanding its behavior and providing you with advice around tracing, distributed tracing, and structured logging, and all of those things. And all of that was great, except you were forced to do all of the work. And customers were asking us, how do I implement this consistently? Have I done it correctly? And everyone was trying to reinvent the wheel. And this led us to the development of Power Tools for AWS. Now, if you're not familiar with this tool, I'd definitely check this out. This is basically what we've done with Power Tools is we've taken all of the best practices guidance that's in the serverless lens, part of the well-architected program, and we've codified it. So you don't have to reinvent the wheel. And now you've got best practices around observability and things like batch processing, item potency handling, which I'm going to mention in a little bit, and all of the other sort of common type of activities that you might be doing as developers, and doing it in a standard way. with best practices applied. And doing that across multiple languages as well, Python, Java, TypeScript, and .NET supported. And now with the release of Lambda managed instances, you've also got full thread safety within those libraries, so you can use that for those applications as well. Now let's have a look at some of the serverless resiliency features that we have. Now, a good place to start would be at the beginning, right? Let's look at the front door and let's see what we can do at an API level to help us protect and make our whole application a little bit more resilient. And that really boils down to regulating inbound request rates. And so you can use the throttling capabilities that API Gateway comes in to help you build more resilient applications. Now, there's multiple levels of throttling that you can apply at an API Gateway level. You can obviously set the account-wide levels, but you can also, and you probably should, as a good practice, really align appropriate throttling levels to each of the stages that you have in your environment, like dev, staging, production. But you can also limit, because not every function, not every API endpoint has the same requirements. You may want to also apply those at a method level. Now, usage plans are also a really, really useful tool if you want to be able to segment based on usage. So, for example, you can create usage plans. The simplest example that I can give you is something like a t-shirt size. You can have customers that are extra large, large or small, and then you can assign particular throttling rates to those usage plans and then align and then give those customers or give those users API keys that then determine what kind of throttling rates that are applied to the requests that they are making. And that is a super useful tool, particularly in if you're building SaaS applications or you're exposing public APIs. Now, of course, throttling is not the only thing that helps you build resilient architectures. One of the probably lesser known features of API Gateway is the ability to have method level caching for your GET requests. And this is really simply taking off back pressure, so you don't have to make unnecessary calls to your backend for frequent requests for the same information. Now, if you need more fine-grained, control over this, then obviously another strategy you can do from a caching perspective is use AWS CloudFront distribution, and making sure that the requests that are being sent are actually valid requests. Again, this is a little bit more effort that you would put into defining your APIs, but it just ensures that you don't get any bad actors sending you payloads that you're not expecting. And you've got other features like making sure that you clearly define your integration timeouts and that you obviously secure your API through some kind of mechanism that's relevant for your application. Right. We're going to get into some Lambda stuff, but before we do, I just wanted to level set our understanding around what synchronous and asynchronous means. So these are very common terms, sometimes misunderstood. For us today, it basically means synchronous requests are basically where a caller waits for an immediate response before continuing. Right? It is basically expecting the client is basically expecting the service to finish its work before responding. Okay? Now, some of the, drawbacks to this approach is that you have all of the latency, all of the failures, and all of the back pressure fundamentally become the responsibility of the caller. Now, with asynchronous invocations, what we're really talking about is managing sort of the temporal nature of our interactions, where the caller doesn't have to wait for the service to finish. It just continues on and does what it needs to do. And at some point in time, the service may or may not provide a response. And this is a much safer way of building serverless applications, but it also brings in some complications around making sure that you've got explicit correlation between for requests. So any asynchronous interacting components or services can be traced back to the original call. And you might look at things like eventual consistency as a mechanism for defining how your users interact with your system, as well as looking at providing separate error paths as well for potential failure. So when we're looking at Lambda and Lambda's resiliency implementation, there's a number of different ways that we interact with that service, depending on the type of integration that you're performing. Now, from a synchronous perspective, this is something we call the push model. This is basically you invoking Lambda directly, right? And the client, as we just defined, is waiting for a response from that function. And it will also return immediate success or response depending on the outcome of that invocation. And we've also got asynchronous invocation, which is really driven by services like events that have been published by S3. You may have SNS notifications, CloudWatch events. EventBridge is also considered to be an asynchronous invocation type. And it's important to understand the difference between this and the next one. But fundamentally, here, Lambda is actually fundamentally queuing all the requests, allowing the caller to continue on and allowing the caller to continue on processing and doing what it needs to do, and the invocations are asynchronously invoked, which means that there is no response back to the original the caller. Now, from an event source mapping perspective, this is where you have integrations with SQS. You have DynamoDB streams, also Kinesis streams. This is where Lambda fundamentally polls the event sources and invokes the functions on your behalf. So it's important to understand that these three different invocation types exist because they will determine how you can potentially architect your solution. Now, from a synchronous invocation perspective, here, Lambda does not automatically retry any potential errors, right? The functions are fundamentally stateless, and there is no durability in these requests either. So if anything goes wrong, your ability to rehydrate any kind of state or get back to where the error occurred is very small. In fact, it doesn't even exist. So this is probably one of those cases where you might want to go, hang on a second, could this be a point in time where that $1 million widget got lost? I'd be thinking about whether or not the synchronous implementation actually is a good idea. Now, from an asynchronous perspective, we have a slightly different approach. You can notice here that I'm not using API Gateway, I'm using EventBridge to invoke my function. And what's happening here under the hood is that EventBridge isn't actually invoking your function directly. It's sending that request directly to an internal AWS queue, and then we have a polling process within Lambda that takes that message and invokes your function. So this is that part of that serverless reliability, like this is all happening under the hood without you actually needing to do anything. And this gives you the ability now to be much more resilient in the sense that you can either use the existing retry mechanisms that exist within this asynchronous invocation, because Lambda gives you the ability to retry up to 2 times, or you can then configure that Lambda function to use either a dead letter queue or a destination. My advice would be to look at dead letter queues, and if you have any questions about destinations, I'm happy to have that conversation afterwards. But it's also, so this is a great, but this is not obvious when you draw that line that we talked about before, because all you're doing is drawing a line between EventBridge and Lambda without realizing what's happening under the hood. Now you know. Now this is something that you can reason about when you're thinking about your next architecture. Now, from a polling perspective, we do something slightly different. So this is actually the same thing as you just saw, except now you own the queue. And this is where you have the ability to define the parameters around that queue and how many retries you might want to configure for that, and various other properties that will help you perform the necessary throughput capabilities that your function needs. But what's happening under the hood is this. Again, you don't have to create pollers. In fact, you can't even configure Lambda today to actually do this yourself. You don't have to create pollers. We create pollers for you. And those pollers are basically pulling those messages off the queue and then invoking your functions in batches. And so there are some trade-offs with this approach. In fact, this is actually, although it kind of looks like an asynchronous invocation, it's actually considered to be synchronous in the sense that the pollers are actually invoking your function directly, even though you're using a queue, which might lead you to some confusion. And so in this sense, you're making some trade-offs where there is no Lambda destination support, but you do have far greater control around the integration with Lambda. And you can then use that configuration to process many more messages in batches. Now, one of the things with this integration is that basically, with SQS at least, the event source mapping basically treats each request as a batch. So you have a batch size that you define, and that batch is either succeeds or fails in its entirety. Now, and that continues, and if your function fails for one of the records in that batch, the entire batch gets put back onto SQS. And this continues up until that point where you've been able to process all the messages successfully, or you've reached the maximum retry attempts, or you have or your retention period for those messages fails. But there is a way that you can look at partial failures within SQS as well. So this is where you would configure the partial batch response configuration, which allows you to effectively, where you need to then create a JSON object that allows you to, which is called the batch item failures, which is effectively a list of all of the message IDs that you would then return as a response back to SQS, and only those messages that failed would be put back on the queue while keeping everything, or while processing everything else. Now, one of the things this is something that you would have to do though, right? You would have to create this list and you would have to send that response back. But what if there was a better way? This is where you might want to start unleashing the power of AWS Power Tools and using the batch processor utility that does all that stuff for you. So in this instance, effectively, when you define or when you use a particular batch processor type, and the Lambda Power Tools actually supports multiple different types of event sources like Kinesis and DynamoDB streams. So you can use the same library irrespective of what event source you're actually using. And then basically, all it's doing is taking the item identifier and building that list for you so you don't have to. And that's a huge saving in terms of like the coding and testing that you need to do. And it's a simple configuration. This leads us on to the next sort of topic around item potency. So item potency fundamentally means that no matter how many times you process the same message, the end result is the same. But why is this important? Well, basically, in a loosely coupled distributed architecture, a producer and a consumer can basically become temporarily disconnected for a number of reasons, but mostly it's related to network-related issues. Think about sort of like the partition element of the CAP theorem. So when a customer might successfully process a request, but the acknowledgement never gets back to the producer of that event or that request. And then the producer is likely to want to retry that request, sending the same payload back to that function. And so this can put you into an inconsistent state. Again, this is where Power Tools can help. Power Tools has an idempotency utility that mitigates the need for you to actually build a solution yourself around how to treat or how to deal with potential retries and help you with deduplication. So in this case, basically, you would get a client invoking a Lambda function. At this point in time, the utility will make a record of that request. It will process and and manage the state for the response. And if anything went wrong, and then a subsequent retry happened, it would simply either return that request that it had stored before, and giving the requester the same response, or it would then continue processing that message in a safe way. And this is really useful for any kind of event source, really, that you might have, such as asynchronous invocations or event source mappings that we've just been talking about, and works great in conjunction with the things like the batch processing utility. All right, now let's look at EventBridge. EventBridge also has a built-in resiliency capability. In fact, by default, EventBridge will actually retry sending messages to its intended target for up to 24 hours or 185 times. And it does this with exponential backoff and some jitter rationalization in there as well. Now, 24 hours might seem like is a pretty long time, but it's there. Like you don't even have to do anything, and already you're getting automatic retry built into the service. But you might want to actually control this a little bit more fine-grained, so that you can now configure your targets to be able to set the number of retries that you want to have in your applications, or how old the messages should get before those are sent to an Amazon SQS queue that you configure. So you've got far more control over how these failure scenarios happen. And the nice thing about the way that those errors are then stored within your SQS queue is that you actually, once you've looked, you actually are given error codes and error messages that help you troubleshoot those potential integration issues that you have. And it could be, someone may have deleted a resource. You may have misconfigured your IAM permissions. This is sometimes hard to troubleshoot, and now you have the ability, and this gives you the ability to do that more quickly. All right. So those are just some of the ways that AWS helps you implement resiliency out of the box. And I've shown you how you can leverage some of the Power Tools capabilities to help you build more resilient implementations. Let's have a look at some patterns for resilience that you can then apply yourself. All right, where are we at now? So far, we've looked at a couple of different approaches. We've taken our kind of naive sort of example, and we've started looking at ways that we can turn this into an asynchronous implementation. And we've got a queue now. We've got some durability in the sense that even if we do fail to process that $1 million widget, we know that it's going to end up in the dead letter queue. That request never got lost, and so you're not going to have a bad day in the office. Now, one of the things that API Gateway, I just wanted to call out, is also probably something that's lesser known with customers, is the ability for API Gateway to actually invoke other services directly. So this is really useful where you may want to be able to bypass the need to have a computational, a comp service like Lambda as a middleman. So the ones that we've been looking at so far is API gateway to Lambda, and that's very typical, and that's where most people start. But when you're starting to build asynchronous architectures, you might want to consider using an API gateway to SQS integration directly, so that your original HTTP request ends up in a queue, allowing you to then process those messages in a time frame that suits you or your application best. Or you might be wanting to invoke an SQS directly, you want to be invoking a step function, right? Without actually having to invoke a function beforehand to then call the SDK in order to invoke that. So this is a really, really useful tool to be able to bypass some of that logic necessary. And effectively what we're doing here is we're taking the raw API calls and then literally just mapping the requests from API gateway into, in this example, a send message API call that then creates the record on the SQS queue. Now another popular approach, and I'm going to do this with an air of caution, is API gateway to DynamoDB, right? All you might want to be doing is manipulating some data or processing some data, reading some data out of the database, which in this case, it might actually be a really useful tool. But I'm cautioning you here to not to do this with things that manipulate state. First of all, this is not a very testable implementation for your API gateway, particularly if you're manipulating state in a database. Okay. The other thing is that anything that manipulates state tends to be, if things go wrong, whose problem does it become? It becomes the client's problem. And what can they do about that? Not a hell of a lot, right? So they typically maybe want to retry those requests, persist that. It's just a bad experience for everyone, right? Now, if you want to read information, that's non-mutating, and I think that's perfectly okay. But if you're looking at this as an approach or as a means of minimizing some of the compute logic that you need, I would just caution you to reconsider that for write operations, perfectly okay for read. Okay. While we're on the subject of reading and writing, let's have a look at this from a transactional perspective. Now, what we've got here is that we've got API gateway, we've got our API gateway integration with SQS, we've got our dead letter queue, we're calling our function, and we're persisting some information. Is this still a resilient architecture? We're getting there, I think. So from the first transaction is this, right? If a client request fails, right, the error from an API perspective is, so what I mean by that is that the message actually never ends up in the queue. Now this is an AWS managed integration, so the likelihood of this happening is relatively small, but in case it does, right, the good thing is that you haven't actually manipulated any of the systems. The system is still in a consistent state. You haven't done anything with the back end. The client maybe is a little bit unhappy because it got an error, but at least you've got some stability in your environment. Now, if it succeeds, then the message will end up in the queue, and the client gets a 200 response saying, thank you very much, and you're basically telling them, we'll take it from here. All right? Which is actually a really good place to be, because anything that goes wrong potentially after this is not the client's problem, it's your problem. And you can then build mechanisms to deal with those problems. So our next transaction is actually writing and taking that record and actually putting it into the DynamoDB table. Again, because we've got a queue, we've got a temporary buffer. So any potential failures that occur around writing that information to the database will only just put that request back on to the queue. So you've got some safeguards there around potential failure. And if the problems persist, then that message will end up in the dead letter queue, and you've basically rescued your $1 million widget from losing that sale. Now, you're not going to just be writing stuff to a database. In an event-driven architecture, you might be wanting to actually notify someone that that $1 million record was just written to the database. So in this case, you might be looking at maybe publishing an event as well. Now, this is potentially a bit of a problem. What do you think is wrong with this picture? What we've potentially introduced here is a distributed transaction, okay, where the function is actually doing two things. Now, if anything goes wrong within your function, that's maybe it hasn't quite written the record to the database. You've published the event, letting everyone know that something occurred that actually didn't occur. Or you successfully wrote something to the database, but you failed to notify other people that it actually happened. Again, it leaves the other systems or other interacting components in an inconsistent state. And so what we want to do is try and re-architect this a little bit to make this to introduce a third transaction that guarantees us or put some guarantees around the eventual delivery of that event. So rather than having the Lambda function actually doing both things, what we want to do is we want to enable DynamoDB streams, which basically is a time-ordered sequence of items that are modified in your database. So if you create a new record, or if you modify an existing one, or delete something, there will be fundamentally a change data capture event on that stream pertaining to that particular record. Now, what you can do here is, ideally, you can do a couple of different things. You could have another Lambda function read off that stream and then process that. But we're now in a serverless space, so we're going to look at event bridge pipes, which allows you to select sources from a range of different services as something that will invoke something that you can use to actually transform the message. Now, why would you want to transform the message? Well, like I said before, this is a change data capture event. This record represents a service level change in your database, but that service level change is not very useful for other customers or other services, right? It has no business representation, and nor has it got the context necessary to tell those recipients that change actually has some kind of meaning. And so what we want to do is you use event bridge pipes to actually transform this information into something useful. So here we can use some of the filtering capabilities for our pipes to only process those events that we're interested in processing, and then using the target transformer capability to convert that DynamoDB record into an event bridge event that has some kind of business representation. And this allows us then to share that information across our environments and allow those recipients to understand the meaning of what just occurred. Now, what I just showed you, one event bridge, I mean, the names kind of give it away, but effectively what this implementation, what the event bridge pipes implementation is a representation of the pipes and filters pattern that was popularized by Gregor Hoppe in his Enterprise Integration Patterns book. And this is basically just an architectural style that allows you to divide a bigger problem into smaller independent steps. Without, and in this case, the recipient really only needs, the message sender really only needs to know around what transport or what pipe to send messages to. It doesn't know or care what comes after that. So this is a nice way to start breaking down problems rather than thinking more sort of like everything has to happen in one sequence. I think that's a really important concept, especially when we start dealing with distributed architectures. Now, another implementation of our pipes and filters, arguably, is using step functions as a means of building resilient workflows. Now, step functions is, if you're familiar with step functions, it allows you to build state machines that, follow a sequence of steps that allows you to, fulfill over a long period of time, some business outcome. And with that comes a whole range of capabilities that help you build more resilient workflows and implementations for your applications, such as error handling. It's got built-in error handling that allows it to actually look at your function level and custom level exceptions that you emit from your function. It allows you to then use that to either for graceful degradation, or allows you to choose alternative processing flows. It also has automatic retries and exponential backoff capabilities. These are things that you don't have to program. You don't have to come up with the algorithms. They're already built into the service, so you can then gracefully manage how you're interacting with other services or components in your workflows. And also allows you to fine-tune those interactions through timeouts and heartbeats, to make sure that those services are available, and also manage potential issues around timeout. So this still leaves us with a bit of a challenge around how do we deal with distributed transactions, okay, where we actually need to complete a series of steps that need to work as a single unit, right? Now, we don't have distributed transaction coordinators in the cloud. In fact, I don't think anyone has, and it's really hard to. So what we need to do is we need to simulate what this looks like. And so this approach is actually, effectively, it was established by Garcia and Molina way back in 1987, this idea of a saga, or what's commonly known as a saga today, but they refer to as a long-lived transaction. And what this allows us to do is effectively build compensating transactions for our workflows, so we can get the entire workflow back to a consistent state. And this is a hugely powerful mechanism for building resiliency and durability into your architectures, and making sure that you really understand what are the consequences of failure within your business processes, and how do you roll any changes that you may have made to a system through various different transactions in your workflow, how do you roll them back? And so this is where you build these long-lived transaction implementations, these saga implementations that have specific steps to do that. And so that's a very powerful mechanism there. All right. We're getting close to the end. What about validating resiliency? We've looked at some patterns. We know that our services have capabilities that may not be obvious, but we know that they exist now, and we can reason more explicitly about that. But how do we validate that? Now, of course, there's lots of different ways that you can test your applications, but one of the things that have become really popular, and now also for serverless, is the ability to do things like chaos engineering. And the chaos engineering capabilities here are fundamentally, they're supported by our service through the, hang on a second. There you go, the fault injection service. But ultimately, what we want to try and do is look at ways that we can manipulate state or the behavior of our underlying system by introducing things like timeouts and cold starts, and manipulating the network so it actually creates errors or fallbacks in our environment. Or we might want to mess around with some of the code dependencies that our functions have, and also to determine what is the outcome of all of this. How can we, if this happens in production, how can we get back to a safe space? And this is where the fault injection service can help you, test some of that. And so it's got built-in capabilities that help you fundamentally manipulate latency. You can do HTTP response manipulation, and you can also force particular failures to see how overall your system behaves when things aren't going down the happy path. All right. So the key takeaways for today's session really are the main things that we sort of started with. Now, this is a quote from Tim Bray who used to work for AWS, who used to be is now an independent technology and author. But he's got a popular saying if your applications are large scale and distributed and don't have any messaging services, it's probably a bug. This is also a really good key indicator that you may not be building resilient architectures. If you're looking at a serverless architecture and there aren't any messaging services in there, you might want to consider or be more explicit about how you're going to deal with failure and where you're going to get durability and reliability from if things go wrong. And so going back to our original question, what's more important? Every message, every widget is important, right? We can't make choices around specific types of requests that come through. We can prioritize and we can, we can potentially reason around, the potential importance of where we put things, but ultimately every message is important. And it's not just about what connects the services that's important, but the actual services themselves. All right, and again, take note of this: two boxes in a line architecture. Think about this the next time you're looking at an application architecture and go, hang on a second, what assumptions am I drawing when I'm looking at a line being connected from one service to another? And ask yourself those questions. Now, we've got some other sessions that you can check out that are along the same theme here. We've got a session, I think it's a breakout session around understanding how to implement circuit breaker, sagas, and strangler patterns. We've also got the Serverless Developer Experience Workshop, which will give you actual hands-on experience, dealing with some of the patterns, as well as a lot of event-driven approaches to building resilient architectures. That's this afternoon here at the MGM. And we've also got integration patterns for multi-tenant systems. That's also worth checking out, and that's tomorrow. Finally, here are some resources around application integration and serverless resources. All of this and more is available on Serverless Land, and we've got a huge amount of patterns available for you to consume on that website as well. And with that, I'll say thank you very much, and enjoy the rest of your day.